All right, in this video, we're going to put everything together that we have learned so far about these different carboxylic acid derivatives. And we're plotting here the energies of the reactions on an energy scale, so for these different acyl groups. So let's just look at what we have in this picture. And if you haven't already, if you're working on digital notes, you can download this picture. I uploaded it to Top Hat. Or you might copy down the structures in your physical notebook so that you can kind of fill in the blanks here. So let's look at what's present here. We have on the y-axis standard free energy. So we're looking over here. Standard free energy. So we're increasing in energy. The y-axis is showing increasing reactivity. Now we have even more information though within this plot here. This is showing 4 different reactions from the acyl group. So look, we have for each of these, this acyl group, we're going to fill in for these different structures what belongs right there. So there's 4 here. And then for each of these reactions, we're forming some transition state. So now here's a transition state for one, here's a transition state for another, transition state for another. So to go from the acyl starting materials that are shown at the bottom, all of these, to each transition state, there is a certain amount of activation energy required, and that's what is represented by these plots. So there's the activation energy. So using what we know, let's start with the transition states. We'll fill in what's missing for the transition state structures. Now we said in the last video that we're going left to right across our list here. Amides have the lowest stabilization of the transition state. Acid chlorides have the most stabilization of the transition state. So that means acid chloride transition states are at a lower energy than amides, and then we can fill in molecules in between. So if we look down at this plot here, the lowest energy transition state, which is a result of the increasing polar stabilization of the transition state, are for acid chlorides, and the lowest energy one is shown at the end here. So that means right here belongs a chlorine for the transition state for nucleophilic addition for acid chlorides. Then slightly more stable due to polar stabilization are the anhydrides. So we can add this to the transition state structure. Next is esters, and next are the amides. So amides have the least amount of polar stabilization of the transition state, so they have the highest energy transition state. Now we can trace this back down to fill in and complete the structures of the acyl groups down at the bottom here. They are represented in increasing from right to left resonance stabilization of the carbonyl compound. So the most resonance stabilized structure is our lowest energy structure, and that is our amide, or NR2 really. And then next are the esters, next are the anhydrides, and last are the chlorides. So we can write the functional group names here. So we have amides, and then esters, and then anhydrides, and then acid chlorides. Okay, so with all of this information, with this plot, we can explain why acid chlorides are more reactive than anhydrides, which are more reactive than esters, which are more reactive than amides. So let's look at amides. We have the lowest energy starting carbonyl compound due to resonance stabilization, and we have the highest energy intermediate because there is a lack of polar stabilization. So that means for an amide to go through nucleophilic substitution, a larger amount of activation energy is required for that to occur. So to overcome that activation energy, an acid or base is needed and heat is needed for this substitution. So we cover that in the very first video for today. Now moving on to esters. The starting material, carbonyl, is a little bit less stable due to less resonance stabilization from the oxygen, and the intermediate is a little bit more stable because it has more polar stabilization of the transition state than amides. So that means when esters go through nucleophilic substitution, we do have quite a bit of activation energy needed, but not quite as much as for amides. And then the trend continues for anhydrides and acid chlorides. Anhydrides have less resonance stabilization of the starting carbonyl compound, so the starting material energy is higher, and that means that's already more reactive than esters and amides. And then the intermediate is more stable than the intermediates for esters and amides because of the increasing polar stabilization of that transition state. And then lastly, acid chlorides are the least stable carbonyl starting materials, so they're existing at a higher energy than the other starting materials. They are already more reactive than the others, and then they have the most stable transition state due to that polar stabilization. So all of this put together helps us understand the reactivity of these different starting materials, the different acyl groups, and why for some acids or bases are required and heat might be required as well.